So let's in this lecture let's talk about carbon nanotubes. Okay, so carbon nanotubes, as the name itself suggests, they are hollow carbon fibers. So what is a tube? Tube is a hollow fiber, right? You can also look at it this way, that if you take a graphene sheet and you roll it up, then what you get is a tube-like structure, hollow cylinder. Basically, that is what we are talking about. Okay, so from the two graphene lectures, now you already know what are NM notations, and you also know that you can have, when you make tubes, then you can have armchair type of tubes, you can also have zigzag type of tubes, and you can also then have a mixture of the two, which is known as the chiral carbon nanotubes. Okay, now we are still talking about single walled carbon nanotube. So whenever we were till now, whatever we discussed, the rolling up the graphene sheet and so on, then we are still talking about just one graphene sheet, and then we roll it up, so we get what is known as the single walled carbon nanotubes. Now you can also have multiple walls. Multiple walls means multiple concentric cylinders. So we are talking about one cylinder, but we can also have multiple cylinders. In that case, you can call it multi-walled carbon nanotubes. Okay, again, like all other carbon materials, this material also has a history. This material was also reported in the past. Even there have been publications in the 1950s and 60s where at least hollow filaments were reported. So the name carbon nanotube was probably not used, but hollow filaments were definitely reported. And also, you see, whenever there is vapor of carbon, and then there is also some metal nearby, and there are high temperatures. I mean, that is when you will have vapors of carbon, because when we say vapors of carbon, typically you're cracking a hydrocarbon, or you're performing some very high energy let's say manufacturing processes on graphite, like laser ablation of graphite or any other type of carbon. So in that case, you may have these vaporized carbon atoms, and they contain a very high energy. So at that time, if you also have a metal catalyst present, then 99% you're going to get some sort of carbon. Okay, carbon deposits. Okay, now if these catalyst particles, they happen to be particles and they happen to be in the nanoscale, in that case, the deposits on top of them will also be nanoscale. So you can get these deposits, and ultimately a tube can come up. Okay, so this is basically, these kind of processes were also observed in the near, for example, blast furnaces in the past, because in a furnace you're typically processing a metal. Carbon is almost always present because there is some hydrocarbon that is always present. Sometimes even if you're not intentionally using a hydrocarbon, but you use certain types of oils, or you will use some sort of fuel for the furnace. So from the vapors, somewhere the carbon can always, in some hydrocarbon materials, always present, and then you can find these kind of deposits where you have carbon nanotube, carbon fibers, filaments that are hollow or not hollow. All of these kind of structures can be observed, and they have also been analyzed and reported in the past, characterized. So okay, let us get started with this. So as I already now mentioned all of this to you, this is one picture that I have for you from 1952. So this is a transmission electron micrograph of hollow carbon filaments, which was published in a Russian journal. Okay, so here I have mentioned also. So recently it was published in a review article. So I have mentioned both the review article and the original publication. The point is that these reports were already there in the 1950s. Okay. And what is also interesting is that transmission electron microscopy also existed in the 90s. So actually, this electron microscopy has also its own history. Already started in the 1930s, and it was in a reasonably advanced form already in the 40s and 50s. Anyway, okay, so let us talk about carbon nanotubes. One interesting thing about it is that although for understanding the crystal structure, we often say that these are rolled up graphene sheets. And this is because that makes it easy, for us to understand, okay, especially also in the terms of NM notations and so on. But chemically, these tubes are more closely related to fullerene-like structures. Why? Because these are curved structures. So you know that we have curved carbon structures. This is, one schematic of some spherical structures, spherical carbon structure, let's say Buckminster fullerene. Okay, and now you see this is your tube, which is capped at one end. So I'm talking about capped tubes. Most of the tubes are actually capped at one or both ends, but you can also have open cylinder like tubes. Okay, So, but when you have the cap, now what you see is this curvature in the bottom. The same thing that you see in the fullerene. Okay, what does this mean? This means that you have to have some non-6 membered rings, right? Only then you will get this kind of curvature. So this is actually a type of curved carbon, and in fact that is the reason here and there you will even find that carbon nanotubes are fullerenes. You know, you find these statements, the carbon nanotubes are fullerenes. So don't get confused. This is also, this is how we learned in this course, that carbon nanotubes are a part of the fullerene family, because of the fact that their hybridization state is not necessarily sp2 type but of sp2 plus n type. So if you yeah, that is why this lecture where we talked about sp2 plus n type materials, you should also definitely go over it one more time for you to understand that if in order to have this kind of curvature, you should have some kind of non-sp2. If you have completely sp2 type hybridization, then you're going to have completely flat structures. Okay, so here it is also important that definitely in the case of capped carbon nanotubes, we have some non-6 membered rings, but what about the those which are open on both ends, just rolled up graphene sheet? In that case, well, also there is a certain curvature because we are talking about a cylinder here, right? So again, there is, in this direction, there is definitely some curvature, right? So we still don't have a pure sp2 type hybridization. We have still sp2 plus n. However, in that case, the value of n can be much smaller. Always compared to a completely closed structure, you're going to have the value of n that is much smaller. But you will not have a perfect sp2 hybridization in the case of carbon nanotubes. Okay. Fine. So what else? Yeah, so the point is that I told you that carbon nanotubes and similar structures were observed on blast furnaces and here and there, but still dedicated efforts to understand carbon nanotubes and their utilization in technological application. That only started after, let's say, 1985, because in 85 fullerenes were discovered. So Buckminster fullerenes, and that discovery really helped the entire carbon community, because it told us that curved structures can also be highly stable, curved carbon structures. Okay, so when we saw fullerenes, then there was also interest again, sort of people went back to carbon nanotubes, like, yeah, we also have seen tube-like structures. So then, and also by that time, transmission electron microscopy had become a very common technique, although it did exist in the past also, but in the past only very few universities had TEMs. But then by 1980s or so, it became more and more common technique. Nowadays pretty much many universities have TEM setups. Okay, so this after 1985, then many people started working on carbon nanotubes, and especially one particular paper that is worth mentioning is the paper by Ijima. So this paper, it was published in 91, I think, and this paper actually sort of helped a lot in making carbon nanotubes more popular. Okay, there are many other publications as well. As I mentioned, that I will not go more into the details of the history of carbon nanotubes in this lecture, but similar to graphene, you can definitely find it. If you're interested, then there are many resources which talk about the history of carbon nanotubes. Okay, so the applications of carbon nanotubes, again, I will not go into the details because there are so many applications of this material. What you need to understand is, okay, we already know that electronic properties of this material are interesting. Something that can be conducting and semiconducting, and if you join one conductor, one semiconductor, then you can get these, single element conductor semiconductor junctions. There are so many things that you can do with it. So already there are a lot of electronic applications, especially field effect transistors are their carbon nanotubes are used a lot. There are various other different types of sensors can be made using carbon nanotubes. There are electrochemical applications. They can be used as single tubes as well as the bundles of tubes or the forests of tubes. When a lot of tubes grow together, parallel to each other, then what you get is that is what you call a forest of carbon nanotubes. Okay, so vertically aligned carbon nanotubes. You can also get not aligned carbon nanotubes. That will depend on your CVD parameters. So we are going to talk about CVD after a couple of slides. Okay, so the idea is that you can use carbon nanotubes for a lot of applications. What is also interesting is the mechanical strength of carbon nanotubes. It has been predicted that it is thousands of gigapascals. Not this has not been experimentally validated, but there here and there are scattered studies. But the idea is that if you think about it, when we were talking about carbon fibers, so let's compare the, because it's fiber-like structure. So let's compare it with carbon fibers. Carbon fibers, why do they have cracks? And, whenever we were talking about the, weaker links in your carbon fibers. So why do you have weak links and weak points? Because these are the points where you have voids of some kind. Or because you were deriving the carbon fibers from polymers by heat treatment of polymers. There is a higher probability of containing defects. So defects and voids, these are your weak links. And those defects can come all the way from the polymer, in the beginning itself, if you had some lump of polymer or something like that. So that is the reason, that is where your fibers can break. But that is not the case, with carbon nanotubes, because in most cases, carbon nanotubes are prepared by bottom-up processes. This is an atom-by-atom deposition. Or if not atom by atom, at least it is smaller units coming together, so it is a bottom-up process. And in the case of bottom-up processes, the defects are much, much less. And especially when you have extremely thin walls, whether it is single or multi-walled carbon nanotubes, you have very thin walls of these tubes. There, it is not even possible for very large defects to exist. Even in the case of carbon fibers, when as we keep reducing the diameter of the fiber, at some point what we have is the defects cannot be there anymore, because that becomes a very high energy structure then. So that is why it has been predicted that carbon nanotubes have thousands of gigapascal, that is the Young's modulus. Okay, but some of it has been experimentally validated, some not, because also you can imagine that you have these extremely thin structures. Single walled carbon nanotubes can be 1.72 nanometer in diameter. The aspect ratios are typically high for carbon nanotubes. Even there have been reports of several centimeters long carbon nanotubes. But the point is that it's also a very sensitive thing. If you have single-walled nanotubes, if you have multi-walled nanotubes, already the properties differ a lot. Also, the electrical properties differ a lot. So you learned that when you have zigzag type carbon nanotube, in that case, what happens is when the face of your tube is zigzag type, the path that electron needs to take, that is perpendicular to it, right? The path during the electrical conductivity. So for the zigzag type carbon nanotubes, you actually have armchair type of path for the electron. And for the armchair type of carbon nanotube, you actually have a zigzag path where electron can easily travel. So these type of carbon nanotubes are then pretty much always metallic. And the zigzag type, however, can be metallic as well as semiconductor. So zigzag type, when I say the path of the electron is armchair type. Okay. And the chiral nanotubes, they can also be both semiconductor and metallic. In most cases, they are metallic because once the diameter of the tube increases, in that case, they are more, towards being metallic rather than having a band gap. Okay, so all of these things we will discuss briefly. Okay, because of the mechanical strength of the carbon nanotubes, whether it is validated experimentally or not, but the point is that carbon nanotubes are already extensively used in composite materials. So you can add tubes directly, like what we did with the short fibers, or you can also make ropes of carbon nanotubes. Now you have strands. And with the strands, you can either braid the strands and then make these nice preforms, or you can directly also add these strands inside your polymer matrix. So you can also make carbon-based composites. So carbon nanotube reinforced plastics. That's also a new and advanced area of research. Okay. So here are some more publications. So the one that I mentioned, the EGMAS publication, and also pretty much at the same time, Bethune et al. Also published a paper in Nature. So these two papers actually are very, commonly cited when it comes to carbon nanotube. Okay. So now let us talk more about the properties, and then we'll talk about the manufacturing. Okay. So about the properties of carbon nanotubes. So I already mentioned that you have single-walled carbon nanotubes, you have multi-walled carbon nanotubes. Now these things, these properties, also the electronic properties, can also be used for classifying your carbon nanotubes. So couple of different types of classifications that I have mentioned here. So one is based on the number of walls. So here probably with this picture it will become more clear that you have a single cylinder or you have concentric multiple cylinders. Yes, one important thing is that these multiple cylinders, if you see it, a cross section, then they are not ABABA type arranged. They are turbostratically arranged. So they are not. There is no 3D crystal geometry. Okay. Also because it is a carbon structure, so it is difficult for such structures to have a 3D arrangement anyway. Okay. So this is one type of classification. The second one is based on the chirality. So we already talked about chiral and achiral type carbon nanotubes. There are two achiral type of carbon nanotubes, zigzag and armchair, and the chiral ones are everything that is not zigzag or armchair, or whenever it's a mixture of the two. Then so there is, you can imagine there is a higher probability of finding chiral nanotubes, and also zigzag armchair. These geometries only exist when you have a single walled carbon nanotubes and not in the case of multi-walled. So often in most cases what you have is a chiral structure. Now, by the way, what is a chiral structure? What is achiral structure? So achiral structure is something that can be superimposed on its mirror image. Okay. And on the other hand, chiral cannot be superimposed on its mirror image. So this is the definition. So basically, sometimes people also explain it with handedness or not. But in terms of chemistry, this is the definition. So if you have the mirror image, so you can imagine that for the zigzag type of carbon nanotubes, you can superimpose it on its mirror image, and that is why that is known as achiral. And the others, when it is a mixture, then it's difficult to. So the left will look right in the mirror, and you cannot superimpose it. Okay. So again, I have drawn these two images here, and what you can see, what I was also mentioning before, is that if you have a zigzag type of geometry here, okay, so this is your zigzag type of carbon nanotube, but if an electron has to flow through this, then there is no zigzag path, if the electron moves into this direction. So in that case, you can see that there is, now the path is not zigzag. On the other hand, here you see the armchair type starting, or the face of your carbon nanotube is has this armchair symmetry, but here you can find the zigzag path for the electron to travel during electrical conductivity. Okay, so fine. Now here please also look at the lecture on graphene and also the crystal structure, where we also talked about the NM notations and so on. Okay, what else? So this was the classification based on the structure, crystal structure, as well as number of walls. What else? We can also classify carbon nanotubes based on their properties. So I already mentioned that you have either semiconductor type carbon nanotubes or you have metallic type. So this is already a very easy way for us to classify. However, what is also interesting is the reasons for carbon nanotubes to be semiconductor. We know a little bit about the path of the electron. We know a little bit about the zigzag and armchair type symmetries and where it is easier for the electron to travel. However, one thing is that as the carbon nanotubes become larger in terms of diameter, as their diameter grows, even if they are single walled, although single walled carbon nanotubes typically do not have much larger diameters, because then their formation becomes difficult, their enthalpy of formation goes very, very high. But still, whenever you have larger diameter carbon nanotubes, they tend to be conducting rather than semiconducting. So by the way, in the case of semiconductor, also I will mention the I'll mention the band gap somewhere. Okay, the point is that the conductor nanotubes, of course, they have a zero band gap, and there is a higher probability for you to find them, and that is why we can also this is also one way of classification. Of course, capped and open, this is also another way of classification. Okay, now you learned in the NM notations lecture how to calculate the chiral vector for a carbon nanotube. Okay, so NM notations, again, N is the number of times that you travel along the lattice vector A1, and The other lattice vector, whatever you can call it, A1, A2, whatever. The other lattice vector, whatever distance you travel along that, that is your M. Okay, so I'm saying this A1 and A2 are exchangeable. That is why I'm so N and M don't have to be associated with any, so because you can take your vectors in any direction. It is a 6-fold symmetry in your graphene sheet. Okay, so the point is that N times A1, M times A2 will give you this kind of this chiral vector. So see, this is how you represent your chiral or circumferential vector, and then that is NA1 plus MA2. Okay. So here I have put the vector marks. It should be also on A1, huh? Okay. So the second important the relationship for you is how do you calculate the diameter of a radius of a carbon nanotube. So radius, of course, you have 2 pi divided by so c divided by 2 pi. So c is basically a circumferential vector. So that divided by 2 pi, and then there is this particular formula which relates it to the n and m coordinates. Okay. So these are I have not been very careful with the vector notations here. So just see, C also has a vector notation here. Okay, fine. So here I was mentioning that I will tell you what is the band gap. So 0.4 to 2 electron volt is this. There have been different types of carbon nanotubes. Different lengths also can affect the band gap. And different diameters, of course, influence the band gap. So in different publications, between 0.4 to 2 electron volts of band gap has been reported for carbon nanotubes. Okay. Yeah, so as I mentioned before, these multi-volt carbon nanotubes, because of their larger diameters, they tend to be often metallic rather than semiconducting. Okay, so now in the next couple of lectures, we are going to talk about the fabrication techniques for carbon nanotubes.